also have to be related to the exposure of interest. And by including such confounders in the model, you're including other factors that predict your exposure, that predict your X. And that's going to hurt you. That's going to make your standard error become bigger. If you have many of these potential confounders, you're in this problem of multicollinearity. Multicollinearity means that the factors in your model are related to one another. In terms of epidemiology, that means the factors you have in the model, the other confounders, by definition, are going to be related to the risk of being an exposed person. Males smoke more, males have higher blood pressure, males have higher cholesterol. So if you include in your model not only male, but also include smoking, blood pressure, cholesterol, what you're doing is including other factors that are collinear, that are predictive of a person's gender, predict being a male. That means the standard error of the male term is going to increase. To see that, here's an extreme case of collinearity. Let's forget about talking about males and females. Let's suppose we have two risk factors, systolic blood pressure and diastolic blood pressure, as we do in the Framingham heart study. You would predict or expect a person who has high systolic blood pressure tends to also to have high diastolic blood pressure. They tend to run together. People who are high on one are higher on the other. People who are low on one are low on the other. Well, it turns out in that data set of the 1,363 people, the correlation coefficient between systolic blood pressure and diastolic blood pressure is 0.79. They're highly collinear. They're highly related. What happens if I fit a model with just diastolic blood pressure? Here's a model that says a person's log odds of getting coronary heart disease is V0 plus V1 times his or her diastolic blood pressure. Notice diastolic blood pressure has a coefficient of 0.02, standard error of 0.004, and it's a significant predictor of a person's log odds of getting coronary heart disease. Diastolic blood pressure has a statistically significant relationship to your risk of getting heart disease. Now what happens if I fit a model that has diastolic blood pressure and systolic blood pressure? Notice the coefficient of diastolic blood pressure got smaller. Notice its standard error got bigger. Notice it's no longer statistically significant. In a model, it's already taking into account systolic blood pressure. The reason is, conceptually, if I'm already taking into account a person's systolic blood pressure in terms of predicting his or her risk of getting disease, diastolic blood pressure is not adding much on top of that. It's not an incremental, independent predictor. Once systolic blood pressure is in the model, diastolic blood pressure is no longer significant. And the reason is, or one of the reasons is that the standard error of that diastolic blood pressure term is becoming bigger, because it's harder to judge the independent effect of diastolic blood pressure independently of systolic blood pressure, because once you control for systolic blood pressure, as we have in this model, we're almost controlling for diastolic blood pressure itself, because systolic blood pressure and diastolic blood pressure is so highly correlated. So just realize that if you're controlling for a confounder, you are controlling for a factor which by definition is related to your exposure of interest. And that's going to impact on the standard error of your exposure of interest. It's going to make it bigger. So just like in stratification, if you are controlling for a confounder in stratification, let's suppose we want to know if males are different from females in terms of the risk of getting heart disease, like we were talking about earlier today, like we were talking about last week. If you control for age through stratification, that means you're going to take your data set, you're going to divide it into pieces, old people, middle-aged people, young people. Then you're going to do separate analyses within each of those subgroups. You're going to compare old men to old women, middle-aged men to middle-aged women, young men to young women. That's what you need to do to control for confounding by age with stratification. But let's suppose that age and gender were highly correlated, that the men were old, the women were young. So when you're old stratum, when you're comparing old men to old women, you might have lots of old men and very few old women, because most of you women are young. In your young table, you're going to have lots of young women, but you're going to have very few young men. That means in the stratified analysis, in the old table, you compare old men to old women, you don't have much information. You don't have very many men in that table. So your odds ratio is not going to be very precise. In your young table, you have lots of young women. You don't have very many young men. Again, you have a very imprecise, very unstable table there because you have very few men in that table. Your odds ratio is going to be very imprecise. Standard error is going to be bigger. Even in a model, you control for age, looking at the effect of sex, you might be ending up with a very imprecise result, a very unstable result, if the confounder is highly correlated with the exposure. So it's very difficult in a model or with stratification to control for a strong correlate of the exposure. Very difficult to measure the effect of diastolic blood pressure when you're already controlling for systolic blood pressure, as we have in this situation, because these two factors, diastolic and systolic blood pressure, are so highly correlated. Controlling for one makes it very difficult to look at the independent effect of the other. Among people with very high systolic blood pressure, it's hard to compare people with high diastolic blood pressure to people with low diastolic blood pressure, because among people with high systolic blood pressure, almost everybody has high diastolic blood pressure. Very difficult to measure the independent, incremental effect of high diastolic blood pressure compared to low diastolic blood pressure once you're controlling for systolic blood pressure, because your standard error is becoming large. Well, that's all I wanted to say about precision. And let me end up in this example talking about one last, and the main reason we build these models is, let's suppose we want to control for many confounding factors. So here's a model. Let's suppose I want to look at the effect. Let's change gears now. Let's suppose I want to look at the effect of smoking on your risk of developing coronary heart disease. I want to control for gender. I want to control for age. I want to control for blood pressure. I want to control for cholesterol. Let's suppose this is my model. Now, first of all, let's imagine if we try to do this analysis with stratification. If I want to know what the effect of smoking is on your risk of developing coronary heart disease, and I want to control by stratification, control for sex, I'm going to divide my data set into men versus women. I'm going to break it into two pieces. If I also want to control for age, I have to break those two pieces into more pieces. Say I'm going to take each of the male, I'm going to take the male subset of my data set, I'm going to break it into young males, another piece is middle-aged male, another piece is old men. If I want to further stratify by blood pressure, I'm going to have to take each of those male and age-specific tables and break them into high, middle, and low blood pressure levels. I have to do the same thing with cholesterol. So what happens in stratification? As the number of confounders you want to control for increases, the number of strata you have increases. What that